So in this lecture, we're going to discuss about line of collision. Okay. So for 1D type of collision, the things are more or less simple. Okay. What happens for 2D collision, or how do we apply coefficient of restitution in 2D collision, that we're going to discuss out here. Okay. See, for any type of collision, you can apply two equation. Okay. Conservation of momentum, the first equation, and the second one is coefficient of restitution. Okay. And if it is elastic collision, then you can also apply another third equation, that is conservation of kinetic energy. So for all problems related to collision, you can apply this two equation with additional equation of conservation of kinetic energy for perfectly elastic collision. But what happens when the collision is in 2D? Okay. So in this question, the first part of the collision is in 1D. So learn a little bit of theory. What happens when the collision is in 2D? Okay. See, in collision, you know that you can apply two equations, conservation of momentum and coefficient of restitution. Okay. And if it is elastic collision, you can also apply conservation of kinetic energy. Fair and fine. Asha, one more thing. For 2Ds, remember a question that I did in kinematics. Two bodies will only collide when their relative position vectors is 180 degree to their relative velocity vectors. That means what? The particle will only collide when their relative position vectors are 180 degree to their relative velocity vector. There is a question in kinematics that I did, okay, by same approach, isn't it? So there are two bodies, okay, M1 with V1 before collision and M2 with V2 before collision. After collision, okay, the velocity becomes M1, sorry, V1 after collision, or V1 after collision, and M2 V2 after collision. Okay, how is to apply conservation of momentum? M1 V1B plus M2 V2B is equals to M1 V1 V1A plus M2 V2A. Okay, this was the conservation of momentum equation. Conservation of restitution was you first take the observer out here, okay, then find out the velocity of this object, that is the velocity of approach, then you change the observer out here and find out the relative velocity out here, that was the velocity of separation, and coefficient of restitution is equals to velocity of approach, sorry, velocity of separation by velocity of approach. Okay, so there are basically fundamentally three equation: conservation of momentum, okay, coefficient of restitution, and third one is conservation of kinetic energy for elastic collision only. But when you do 2D collision, no, suppose this body, okay, is colliding with this body M V2B, and after collision, instead of going in a straight line, okay, suppose M1 moved in this direction, velocity of 1a, and M2 moved in this direction, velocity 2a. So you can also apply conservation of momentum out here, okay, and you have to do I cap j cap, and you can further break down the conservation of momentum into I component and j component. Okay, so out here conservation of momentum will have two equations, x component and y component, x component and y component. Okay, but a weird thing happens when you apply the coefficient of restitution. Okay, a weird thing will happen. See, velocity of separation is what? V2b minus V1b. So along this line. But out here velocity of separation, when you apply out here, no, the direction of velocity are in I cap and j cap, and that wouldn't satisfy this equation. See, you can apply it and check it yourself. Okay, it would come out as weird equation. I cap divided by I cap j cap is equals to 1. So it cannot be valid. Okay, you cannot validify coefficient of restitution like this. Okay, so why is that? That means what I'm trying to say is, suppose this angle is theta. Okay, this angle is theta, this angle is theta. Okay, I'll show you the wrong approach first and why I cannot validate it. Wrong approach. Okay, what is velocity of separation? Velocity of separation, take the observer out here. Okay, v2a cos theta minus v1a cos theta. So velocity of separation is nothing but v2a cos theta I minus v1a cos theta I. Okay, what is velocity of, and this is y component of velocity also. So if I take the observer out here, the velocity would be in this direction, plus, or sorry, minus v2a sine theta plus v2 or v1a sine theta j, isn't it? Velocity of approach, see, if I take my observer for velocity of separation out here on the m1 body, the relative velocity of m2 would be in this direction, v1a. Okay, velocity of separation is nothing but this value. Okay, or relative velocity as seen by body 1, or relative velocity of body 2 as seen by body 1. So for velocity of approach you have to change the frame. Okay, I have to take my frame at m2. Okay, velocity of separation, velocity of approach is nothing but this body, or relative velocity of this body as seen by this observer. It is nothing but v1b minus v2b I, v1b minus v2b I. The weird thing that you notice out here is, suppose I say coefficient of restitution is equals to 1 or any other value, you would get velocity of approach is equals to velocity of separation. Okay, see the weird thing that happens out here. If this is equals to this, where does this j component come from? That means is the total j component is equals to 0. Out here it's equals to 0, but you understood the problem that I'm facing. Okay, understood. So well, coefficient of restitution you cannot apply like that. However, there is a workaround to apply coefficient of restitution in 2D. Okay, I'll just erase this. And why was this wrong? I'll understand. See, coefficient of restitution is always applied along the line of contact. Coefficient of restitution is always applied along the line of collision. Okay, now you might ask, sir, what is this line of collision? Okay, see the same diagram. Okay, I'm just removing the observer out here. So M1 collided with M2 to form M1 V1A and M2 V2A. Okay, and let's see this 1D collision. Okay, M1 collided with M2 and became M1 V1A and M2 V2A. Okay, when this particle came and contacted with M2, what happened? This was the surface of contact. No, when the particle collided, this was the surface of contact, isn't it? This was the surface of contact, isn't it? Line of collision would be nothing but this line. Okay, perpendicular to the surface of contact. This is the line of collision. Line of collision. Okay, and whenever you apply coefficient of restitution, okay, whenever you apply coefficient of restitution, always apply coefficient of restitution of velocities, of component of velocities along this line. Okay, along the line of collision. Understood? Coefficient of restitution, the velocity of separation would be, or the component of velocity of separation should be along this line. The component of velocity of approach should be along this line. Okay, but I have another doubt. Sir, you have given us the geometry and you said line of collision is nothing but perpendicular to the surface of contact. But out here, two bodies are there, their final velocities are given. How do I find out this? Means how do I find out this line? Okay, the shape of the geometry is not given, no, in most of the question. So how do I find out this line of collision from the velocities alone? Okay, in your question only the velocities, initial velocity, final velocity would be given. So how do I find out the line of collision? That is the main question. See, if you observe one more thing, okay, velocity perpendicular, or component of velocity perpendicular to the line of collision does not change. Okay, component of velocity, okay, component of velocity perpendicular to the line of collision do not change. So what I'm trying to mean out here is, see the first 1D collision. This is the line of collision, isn't it? This is the line of collision. So you have to apply the velocity of separation and component of velocity of separation along this line, component of velocity of approach or along this line. Okay. So out here the component is the full velocity because angle between them is 0 degree. That's fair and fine. Cos 0 is nothing but 1. See, one more thing. What is the y component of velocity? See, what is the perpendicular line? Y component. What is the component of y component of velocity out here? And what is the y component of velocity out here? What is the y component of velocity out here and what is the y component of velocity out here? Did the y component of velocity change out here? Or did the component of velocity along or perpendicular to the line of collision change before and after collision? Okay, they never change. Understood? So component of velocity perpendicular to the line of collision do not change. Okay, sir, you have given us an observation, but you still haven't answered, sir. How do I find out how is the line, or how do I find out the line of collision? Okay, so there comes our next trick. My main question is how do I find out this line? Now let's pick a body M2. Okay, M2. The velocity after collision was in this line. Okay, and velocity before collision was along this line. Velocity 2b or before collision. Okay. Now my question is, what is the direction of change of velocity, or what is final velocity minus initial velocity? Okay, or what is change in velocity? Change in velocity is nothing but final velocity vector minus initial velocity vector. Or out here, change in velocity vector is nothing but velocity 2a minus velocity 2b, isn't it? Okay, and if I draw that diagram out here, velocity 2a minus velocity 2b would be in which direction? It would be in this direction, velocity 2a minus velocity 2b, isn't it? This is nothing but velocity 2a minus velocity 2b, a change in velocity vector, isn't it? Change in velocity vector. And what did I say? Component of velocity to the line of collision do not change. That means along this line or perpendicular to the delta v. Okay, perpendicular to this delta v. Okay, initial component of velocity along this line and final component of velocity along this line would never change. Okay, understood? And so what is the line of collision? This is the line of collision where all the change in velocity takes place. So line of collision. Understood? Okay, now see. So velocity 2b minus velocity 2a was in this direction. So if you draw a line or line of collision out here, okay, and line of collision out here. Now you can apply this coefficient of restriction formula. For coefficient of restriction, that means v1, whatever this angle is, cos theta, phi, or whatever. Okay, v1b or velocity of approach and velocity of separation. The component of velocity of separation along this line and component of velocity of approach along this line. Why? Because along this line the change in velocity does not take place. Okay, the change in velocity only takes place along this line. Understood? So this is the line of collision where the change in velocity takes place. Understood? And we'll apply this in next question to give you further details of how we apply it. Okay, the first part of the question I'll do it quickly. Okay, part A is nothing but two particles. Okay, m1 with velocity v0 and m2 is static. Static means m2 has no initial velocity. After collision, what did the question say? They fly in opposite direction with equal magnitude of velocity. Okay, v. They fly in opposite direction with equal velocities. Okay, my question is, the question was determine m1 by m2 or determine their mass ratio. So I can easily apply conservation of momentum and coefficient of restitution. So first apply coefficient of restitution equation. Okay, so if I want to take velocity of approach, let's take this observer. Okay, and for velocity of separation you have to change the observer. Okay, So velocity of separation for elastic collision, coefficient of restitution is always 1. Okay, for velocity of separation, or this is nothing but v2, or v have to reverse this velocity out here. So v plus v is equals to 2v, or velocity of m2 as seen by observer m1 is equals to 2v, isn't it? And 2v towards right. Right is positive, left is negative. Upward is positive, downward is negative. Doesn't make a difference. Divided by how much out here? Velocity as seen, velocity of m1 as seen by m2. It is nothing but v naught only. V naught. So from this equation we get v naught is equals to 2v. And I can also apply conservation of momentum. Okay, conservation of momentum, that means initial total momentum, or m1 v naught plus m2 into 0 plus m2 into 0 is equals to m1 or minus m1v plus m2v. Okay, why minus m1v? Because v1 is in opposite direction. Okay, if I apply this one, or m1 v naught is equals to v m2 minus m1, isn't it? Now what was the value of v naught? The value of v naught was nothing but 2v. So m1 into 2v is equals to v into m2 minus m1, isn't it? V and v would get cancelled, or our equation is 2m1 is equals to how much? m2 minus m1, and you have to find out the ratio of m2 by m1. Divide everything by m1. This would get cancelled, this would get cancelled. So this is nothing but 1. Are bhai, this is nothing but 1, this is nothing but 2. Okay, so we'll get equation is equals to 2 is equals to m2 by m1 minus 1, or 2 plus 1 is equals to 3 is equals to m2 by m1. Okay, or m1 by m2 is equals to 1 by 3, whichever you like. Okay, I found out this was the part A of the question, which is simple enough. Now we'll do part B of the question that I have explained a little bit before. Okay, deal with part 2 of the question. Okay, that I was saying about. So mass m1 was initially traveling with velocity v naught and collided with another stationary particle m. And after collision, what they happened is mass m1 flew in another direction v1, making an angle 30 degree with the horizontal, and mass m2 traveling in this direction, making 30 degree with the horizontal. Now you might ask, sir, why did you find this 30 and 30? So it is given in the question. Okay, the particles fly apart symmetrically relative to the initial motion of particle 1 with the angle of divergence 60. That means with the horizontal, this one would be 30, this one would be 30. Okay, fair and fine. So instead of writing 30, I'll just make it theta. Okay, so in future any other question comes other than 30, you can easily do it. Fair and fine. So I was talking about the line of collision. No, what is line of collision, or how do we find out? Take this body m2. Okay, the final velocity is v2 in this direction. Final velocity is v2 in this direction, isn't it? v2. Initial velocity is equals to 0. So the initial velocity is equals to 0 out here. Okay, so v2 minus v1, or final velocity minus initial velocity, would be this arrow, isn't it? That means delta v is nothing but this arrow. So the line of collision would be nothing but along the line of delta v. Okay, so this is the line of collision. Line of collision, and we'll apply our entire equation in this coordinate along the line of collision and perpendicular to the line of collision. Okay, now see, this was the line of collision. Okay, making 30 degree with the horizontal, isn't it? This is the line of collision making theta degree with the horizontal, and this is nothing but perpendicular to the line of collision. Okay, let's draw the horizontal line by different ink. Let me draw the horizontal line by red coloring. Okay, and the white coloring is nothing but the line of collision and perpendicular to the line of collision. So we'll apply our entire equation in this coordinate system. Okay, or in this coordinate system. Fair and fine. So let's name the coordinate. This side is plus, this side is minus, down is minus, upward is plus. So if you apply coefficient of restriction, okay, what is the velocity of separation? So for velocity of separation, if I take my observer on m1, okay, what is the velocity of m2? It would be along this direction v1, isn't it? Now if I extend this angle backward, how much is this much angle? This much angle is nothing but theta. See, if I draw a line out here, this much angle is theta, no? So this much angle is theta, isn't it? So how much is this much angle? This angle is nothing but this angle. They're diagonally opposite, isn't it? So if this angle is 2 theta or theta plus theta, then this entire angle would be 2 theta, isn't it? See, for those who did not understand why I have taken v1 in this direction, it is nothing but concept of relative velocity. Relative velocity means if I put my observer on m1, okay, the velocity of the observer will be added to all the bodies that the observer is seeing in the opposite direction. So velocity of the observer itself is in this direction. So whatever the observer will see, I'll add all v1 in opposite direction to all the bodies that the observer is seeing. That is the concept of relative velocity. And what is velocity of separation? Velocity of separation is nothing but the velocity as seen by this observer of m2, isn't it? So what is this velocity? Along x-axis or along the line of collision, it's v2 minus v1 cos 2 alpha. See, our velocity of separation is applied along the line of collision, okay, and no change in velocity takes place perpendicular to the line of collision, isn't it? So velocity of separation along the line of collision is nothing but v2 minus v1 cos 2 alpha minus v1 cos 2 theta. Okay, what is velocity of approach? Velocity of approach is nothing but velocity of, see, if I put my observer on m1 for velocity of separation, I must put my observer on m2 for velocity of approach, isn't it? I must change the observer. I've already said those before. Okay, so velocity of approach is nothing but velocity of m1 as seen by m2. So m2 itself has no velocity, so the velocity as seen by m1, okay, along the line of collision would be nothing but v0 cos theta. See, if this angle is theta, this angle would also be theta, no? This angle would also be theta. And what is the velocity of approach along the line of collision? It's nothing but v0 cos theta. And if I apply coefficient of restitution for elastic collision is equals to 1, so I can say that coefficient of coefficient of restitution is equals to vs by va, isn't it? Or 1 is equals to vs v2 minus v1 cos 2 theta divided by velocity of approach, which is nothing but v0 cos theta. So this is how we apply equation of or coefficient of restitution in 2D. Okay, or from this we can get v0 cos theta is equals to v2 minus v1 cos 2 theta. This is our equation 1. Okay, and the second equation we'll get from conservation of momentum. Whenever collision is there, you can always apply. First equation is conservation of momentum, second equation is coefficient of restitution, and the third equation, in case elastic collision happens, then you can also apply conservation of kinetic energy, isn't it? So the first equation I got from coefficient of restitution. Now if I apply conservation of momentum, okay, see, conservation of momentum you can apply on this axis also, this horizontal and vertical axis also, or axis along the line of collision. Okay, this is horizontal, this is vertical. You can apply on this axis also, you can apply on horizontal and vertical axis also. Both answer will have the same value, but specifically Okay, whenever 2D or 3D collision occurs, always it's advisable to apply your all the equations along the line of collision and perpendicular to the line of collision. Okay, the equations will be much more solvable. Okay, so always apply or note. Okay, so try to apply all equation along the line of collision and perpendicular to the line of collision. Okay, this is generally a very good practice. Understood? So this will be our x-axis or I cap. This will be our y-axis or j cap. So if I apply initial momentum m1 v naught I cap or cos theta I cap. Okay, m1 v naught cos theta I cap. Okay, this is I cap, this is j cap, isn't it? M1 v naught cos theta I cap, and along the direction, along this direction is nothing but how much is it? Okay, m1 v naught sin theta j cap, or velocity of this particle along this direction or perpendicular to the line of collision, plus m1 v naught sin theta j cap. Okay, is equals to what is the velocity after collision, or what is the momentum after collision for particle 2 along the line of collision is nothing but m2 v2 I cap. Okay, see, particle 2 does not exhibit any motion perpendicular to the line of collision, and particle m1 is nothing but m1. See, what is the value of v1 along the line of collision and perpendicular to the line of collision? Okay, if this is theta, this is theta, so component of velocity or angle this velocity makes with the line of collision is nothing but theta plus theta or 2 theta. So plus m1 v1 cos 2 theta I cap is along the line of collision. Okay, and plus m1 v1 cos, or no, not cos, sine, perpendicular is nothing but sine 2 theta j cap. That means component of this velocity along the perpendicular to the line of collision. Understood? So our first equation came from coefficient of restitution. The second equation came from conservation of momentum. And this conservation of momentum equation I can further classify into x component of conservation of momentum and y component of conservation of momentum. Okay. Now there are few things you might note out here. See, the physics part of the problem is solved. Okay. Now if I solve these two equation, I'll get my answer. But before going to solve these two equation, I must clarify few things. Okay. The first thing to observe out here, see, the y component, okay, or the component of velocity perpendicular to the line of collision of both the particles does not change before and after collision. Okay, only the component of velocity along the line of collision changes. Understood? Okay, see, component of velocity perpendicular to the line of collision does not change for both the particles. Okay, that means what? m1 v naught sin theta j should be equals to m1 v1 sin 2 theta j, isn't it? This is the, or sorry, v naught sin theta j should be equals to v1 sin 2 theta j, or the perpendicular component of velocity along this line should be equals to perpendicular component of v1 along this line. Understood? Okay. Now the second thing is, you might ask, sir, you did LOC taking the you took body B and you took the final velocity, you took the initial velocity. You said that change in velocity is equals to this vector. So line of collision is equals to along this line. What happens if I take M1? I do not want to take M2. What happens if I take M1? See, if you take M1, the line of collision would be the same. Okay, see out here, M1. Okay, not M2, M1. M1. What is the final velocity vector? Final velocity vector was along this direction, v1. Okay, initial velocity vector was along this direction, v0. So final velocity minus initial velocity will be along the same direction, or v1 minus v0 would be along same direction. or delta V would be along same direction. So our line of collision would be the same line. This would be the LOC. See, this line and this line are nothing but the same line. So it doesn't matter which particle you take, the line of collision for both the particles will be same. Okay. The velocity or the component of velocity perpendicular to the line of collision does not change, and you can apply coefficient of restitution only along the line of collision. Okay. And conservation of momentum, you can take any axis, but it is always advisable to use the coordinate along the line of collision and perpendicular to the line of collision. This much is understood. So if this much is understood, after that I have to simply solve this two equation, isn't it? So let's solve this. Now we have got two equations. One was from coefficient of restitution, the other one was from conservation of momentum. And this is my coordinate system. Fair and fine. Now this conservation of momentum or equation of conservation of momentum, I can convert this equation into two further equation. Okay, conservation of momentum in x-axis and conservation of momentum in y-axis, isn't it? So in x-axis, what will happen? All the I cap, so m1 v naught cos theta would be equated with all the I cap. So m1 v naught cos theta should be equals to m2 v2 plus m1 v1 sin 2 cos 2 theta, and all the component of j, okay, and all the y component of velocity would be equated with y component of velocity. So m1 v naught sin theta should be equals to m1 v1 sin 2 theta. So now we have three equations. One is from coefficient of restitution. The second one is conservation of momentum in x-axis. The third one is conservation of momentum in y-axis. And we'll solve these three equations to find out what is asked in the question. What is asked in the question? Find the ratio of m1 by m2, isn't it? So how do I solve it? First I take 3 and 2. Sorry, 3 and 1. Okay. So I'm taking equation 3 and 1. 3 and 1. So before taking or before solving this equation, let's just simplify this equation number 3 a bit. Okay. See, in this equation number 3, m1 and m1 can be cancelled out. Okay. Sin 2 theta can be written as 2 sin theta into cos theta, isn't it? And this sin theta and this sin theta can be cancelled out. So sin theta, sin theta. So I'm erasing all the unnecessary part. m1 sin theta, m1 out here and sin theta out here. Okay, so we are left with v naught is equals to 2v1 cos theta. So equation number 3 becomes v naught is equals to 2v1 cos theta. So I'll write the same equation out here. Now if I substitute the value of v naught out here, v naught is equals to 2v1 cos theta. So what would I get? 2v1 cos theta. Okay, I'm substituting the value of v naught in this equation into cos theta. Into cos theta, this value is equals to v2 minus v1 cos 2 theta. Okay, now cos theta and cos theta becomes cos square theta. So our equation would be 2v1 cos square theta is equals to v2 minus v1 cos 2 theta. Now see, in all my equations, there are two components. One is cos 2 theta and one is cos theta. Okay, so either I must convert all my cos 2 theta into cos square theta, or I must convert all my cos square theta into cos 2 theta. Okay, doesn't make a difference. So let's say cos 2 theta. From trigonometry, you know that cos theta plus theta is equals to cos 2 theta, which is equals to cos A cos B minus sin A sin B. So it should be cos square theta minus sin square theta. And because sin square theta plus cos square theta is equals to 1, sin square theta can be written as 1 minus cos square theta, isn't it? And if we equalize this, cos 2 theta should be equals to how much? 2 cos square theta minus 1. See out here, cos 2 theta minus of minus cos 2 theta. So cos square theta plus cos square theta, 2 cos square theta, and minus 1 becomes out here. Okay, so cos 2 theta is equals to 2 cos square theta minus 1. So if I want to find out the value of cos square theta, okay, so cos square theta would be nothing but cos 2 theta plus 1. I have taken the 1 to the left hand side, is equals to 2 cos square theta and divided by 2, isn't it? So cos square theta is equals to cos 2 theta plus 1 divided by 2. Now if I substitute the value of cos square theta out here, what would I get? So I would get somewhat this value. Cos square theta is substituted by cos 2 theta plus 1 divided by 2. These 2 and these 2 would get cancelled. Okay. Now if I expand the left hand side, v1 into cos 2 theta, v1 into v1. Now I can bring this v1 cos 2 theta to the left hand side. So it will become 2v1 cos 2 theta, isn't it? If I bring this v1 cos 2 theta to the left hand side. So I get the equation v2 is equals to 2v1 cos 2 theta. So I've written this entire term out here. Okay, I'll be erasing this one. Now in the second part of the equation, I'll combine 2 and 1. Okay, equation number 2 and 1. So this is equation number 1, this is equation number 2. So if I substitute v0 cos theta is equals to v2 minus v1 cos 2 theta out here. I'm substituting the value of v0 cos theta out here. Okay. So if I substitute the value of v0 cos theta out here, I get this equation, isn't it? Now I'll just expand this term m1 into v2 into m1 v1 cos 2 theta. Now I'll separate out v2 terms and v1 terms together. Okay. So v2 will be sent to the left hand side and this v1 would be sent to the right hand side. See, on the right hand side, m1 v1 cos 2 theta plus m1 v1 cos 2 theta would become 2 m1 v1 cos 2 theta, isn't it? And on the left hand side, we can take v2 common, it would be m1 minus m2. So you would get something like m1 minus m2 into v2 is equals to 2m1 v1 cos 2 theta. So I'll just clean this out. Okay, I'll just write this equation out here. Now we got two further equation, one from the compilation of 1 and 3. Okay, this is 1 3 and this is nothing but 1 2. Now if I combine these two equation, okay, I'll get the value of m1 by m2. So let me combine these two equation. So this equation is nothing but this one and this equation is nothing but this one. Okay, in the bottom equation, if I multiply the left hand side and right hand side by m1 minus m2, okay, I can easily say that I just simply multiply left hand side and right hand side by m1 minus m2. I can easily say that m1 minus m2 into v2. So this value should be equals to this value, isn't it? So I'll just write it down. Now let me just expand this term. Okay, m1 into 2v1 cos 2 theta plus m1 v1 minus m2 into 2v1 cos 2 theta minus m2 v1. Now I can cancel out this term and this term, isn't it? And see, if I take v1 common, okay, see, it will be 0 out here and m1 v1 minus m2 v1 cos 2 theta minus m1 v1 is equals to 0. So I can take v1 common from out here, no? So instead of taking v1 common, let's just simplify this one. Okay, this became is equals to 0, isn't it? Now what do I need to find out? I need to find out the value of m1 by m2. So divide left hand side and right hand side divided by m1. Sorry, m2, not m1, m2. Okay, divided by m2. Out here m2. Out here also m2. So this would get cancelled and this is already 0. Out here also I have to divide by m2. Okay, so if I rewrite this equation neatly, it would become 0 is equals to m1 by m2 into v1 minus 2v1 cos 2 theta minus v1, isn't it? I'm just writing this equation neatly out here. And I need to find out the value of m1 by m2 that is asked in the question. Okay, or m1 by m2 v1, I've sent the entire this thing to the left hand side. Okay, is equals to 2v1 cos 2 theta minus v1, isn't it? Sorry, plus v1. Okay, this also goes to the left hand side becomes plus, this also goes to the left hand side becomes plus. See, I can take v1 common from out here, no? So if I take v1 common, v1, okay, I can cancel out this v1, isn't it? So I'll get the equation m1 by m2 is equals to 2 cos 2 theta plus 1. But the value of cos 2 theta was nothing but 60. Out here instead of, they have taken theta, no? But in my question I have taken this angle as theta. So I've taken the half angle as theta. So out here 2 theta is equals to 60. Understood? So cos 60, 2 into cos 60 is nothing but 1 by 2 plus 1 is nothing but 1 by 2. Or m1 by m2 is equals to 2 into cos 60, or 2 into 1 by 2 plus 1, which is nothing but equals to 2. In this question, what is happening is a ball of mass m is there. It is moving horizontally with velocity v. Okay, and it collided with another stationary ball of same mass. Okay, the question is saying after collision, okay, when they meet together, if I join a line connecting the center of the two balls, okay, this line and the horizontal means the direction of initial velocity, okay, the angle between this line and the horizontal is nothing but 45 degree, that is given in the question. Okay, fair and fine. See, from this diagram I can easily say, no, this is the line of collision. If I join the centers, that means what, this is tangent and this is nothing but the normal. Okay, so this is nothing but the line of collision. Okay, and the question is saying at that time of collision the kinetic energy of the entire system was converted to deform the body. Okay, that means two balls or two rubber balls collided and maximum amount of kinetic energy was converted to deform the rubber balls. Okay, and after deformation what happened? After deformation again they separated, with different velocities. Okay, I don't care what this velocity is, let's say v3, v4. That means if you apply between first scenario before collision and the last scenario, okay, first scenario and last scenario is perfectly elastic collision. Okay, understood? If you apply the equation between first and last, it is perfectly elastic collision, but that wouldn't happen the case between first and second. For the first and second, if you apply equation between first and second, the type of collision is perfectly inelastic. And why is that? You might ask for why. Okay, let's compare this scenario with two balls. Okay, have you seen that problem? A mass m is traveling with velocity v. Okay, another spring mass system is kept out here which is at rest, then they both collided. Okay, and the spring got compressed, and after compression they both the blocks flew separately with different velocities, isn't it? Isn't it? So what is happening if you apply equation between the first and the third? This is perfectly elastic. But if you apply equation between first and second, okay, this is perfectly inelastic. That means maximum amount of kinetic energy of the system was used to compress the spring. Okay, maximum amount of kinetic energy from the system was used to compress the rubber balls. Understood? Now in this scenario, okay, in this scenario, just tell me what was the condition at the time of maximum compression. So the time of maximum compression, the relative velocity of both the blocks with the relative velocity of one block with respect to the other block should be equals to 0, isn't it? That means the spring is not going anywhere. So if the relative velocity of the blocks is equals to 0, both the blocks should be moving with same velocity, isn't it? Okay, so both the blocks move together after collision. So between this one and this one, the collision is perfectly elastic, no? Initially they are moving with different velocity. Velocity of approach is v, velocity of separation is 0. The relative velocity out here is equals to 0, so the velocity of separation out here is 0. So this is perfectly inelastic collision, or the coefficient of restitution out here is equals to 0. If I apply equation between this one and this one, the coefficient of restitution is equals to 0. This is the same problem as this one. So at the time of maximum compression, the relative velocity between both the bodies would be equals to 0. Fair and fine. But the difference between this problem and this problem is, this is a 1D problem, okay, and this is a 2D problem, isn't it? So what is the difference? See, coefficient of restitution you can only apply along the line of collision, no, isn't it? That means what? That means during collision, the component of velocity of this block along the line of collision is equals to component of velocity of this block along the line of collision. Okay, so the component of velocity along the line of collision would be same. Understood? And the component of velocity perpendicular to the line of collision would be same as initial component of these velocities. Understood? So if this is the line perpendicular to the collision, okay, this is perpendicular to the collision and this is the line of collision. Okay, this angle is 45 degree, isn't it? It doesn't matter where you take the coordinates. You can take the coordinates out here also. It doesn't make a difference. Okay. So now we'll apply our equation. Okay. So at time of collision, okay, this is the line of collision, no? Okay. So what is the perpendicular component? Perpendicular component is nothing but v sine 45. V sine 45. What is the line, or what is the component of velocity along v cos 45? Okay, so if I component this velocity around perpendicular direction, it would be this one, isn't it? Now see, the perpendicular component of velocity or perpendicular component of velocity to the line of collision never changes. That means even after collision, this component would be v sine 45. Okay, and this component, the vertical component of this velocity was equals to 0 because this body was rest, no? So the vertical component of velocity would be 0. The vertical component of this velocity also would be 0. Understood? The vertical component of velocity to the line of collision never changes. What will change? Only the component of velocity along the line of collision. And during collision, for perfectly inelastic, both the bodies will have same velocities along the line of collision. So v cos 45, if I apply conservation of momentum along the line of collision, okay, conservation of momentum along line of collision or x-axis, okay, is nothing but v cos 45 plus 0, this body has 0 velocity, no, is equals to, or mv cos 45 plus 0 is equals to m, acha, m, let the velocity after collision be, acha, mv cos 45 plus m v1 or mv1 cos 45 plus mv1 cos 45. That means this body was moving with velocity v1 or v1 cos 45 plus v1 cos 45, v1 cos 45, isn't it? Okay, both the bodies will have same velocity. So if I solve this one or if I solve this equation, what would I get? I would get this value. Okay, when I simplify this equation, or x component of conservation of momentum. So I can cancel out cos 45, mass and mass, isn't it? So I would get v is equals to 2v1. V is equals to 2v1. So velocity after collision, or I can simply say that velocity after collision v1 is equals to v by 2. Okay, so out here I can substitute the v1 and v1 by v by 2. So this is nothing but v by 2 and this is nothing but v by 2. So v by 2 cos 45, v by 2 cos 45. Okay. So velocity after collision in x component of this block is v by 2 cos 45, of this block is v by 2 cos 45. Okay. Then maximum amount of kinetic energy is converted to deform the rubber balls. Okay. Note one thing again and again. Okay. For inelastic collision in 1D, the bodies will move together. For inelastic collision in 2D, okay, the component of velocity of both the bodies along the line of collision would be same. The bodies would not move together. See, this body has a vertical component of velocity and this body has no vertical component of velocity. So will these bodies move together? No. Even though the component of velocity along the line of collisions are same, okay, the total velocities are different even for inelastic collision for 2D and 3D. Okay, so only for 1D after inelastic collision the bodies stick together. Understood this much? Now I have to find out what amount of kinetic energy was converted to potential deformation energy. Okay, so what is initial kinetic energy? So let me erase this one. Initial kinetic energy, you can either do half mv square or half mv cos 45 square plus half mv sin 45 square. Both will have the same value. Okay, just check it. Half mv square, or you can separately add half mv cos 45 whole square plus half mv sin 45 whole square, which will be equals to this value only. Okay, because sin square theta plus cos square theta is equals to 1. So if you component and add the kinetic energy, it will be same as the total kinetic energy. Okay, what is the final kinetic energy of the system? See, initial kinetic energy was half mv square plus 0. Final kinetic energy is equals to how much? For this body, it is half mv sin 45 square plus half mv by 2 cos 45 whole square. Okay, and for this body, it is nothing but half mv by 2 cos 45 whole square. So if I take half m common out here, I'd get this value, isn't it? Now if I expand this one, v square sin square 45, v by 2 whole square, that means v square by 4 cos square 45 and v square by 4 cos square 45. Now out here, I multiply by 4 and divide by 4. Okay, why? Because to take the LCM as 4, isn't it? And if I take now LCM, the LCM would be 4, isn't it? Now it is 4 v square sin square 45 plus v square cos square 45 plus v square cos square 45. So I can add these two, or 2 v square cos square 45. See, now I already know sin square 45 is equals to cos square 45. Okay, because sin 45 is equals to cos 45. But I will not be doing that because suppose instead of 45 another angle was given. Okay, then you would get confused. So I'm solving sin as separate and cos as separate, even though sin 45 is equals to cos 45. Okay, for this question. Now see, v square, this sin square 45 and cos square 45. So instead of sin 45, I'll write them as theta. Okay, because instead of 45, what happens if they give other angles? Okay, so this now becomes 4v square sin square theta plus 2v square sin square theta, and 4v square sin square theta can be written as 2v square sin square theta plus 2v square sin square theta. So this is nothing but 2v square sin square theta plus 2v square sin square theta. Okay, now between these two, if I take 2v square common, cos square theta plus sin square theta is equals to 1. So this entire term would become 2v square, isn't it? Now if I take 2v square common from both this term, it would be how much? Sin square theta plus 1, isn't it? Into 2v square, isn't it? So if I write the total kinetic energy or final half m into sin square theta plus 1 into divided by 4 into 2v square, isn't it? 2 and 2 would get cut, so it would be mv square by 4 into sin square theta plus 1. So out here final kinetic energy out here, or final kinetic energy of the system, is nothing but mv square by 4 sine square theta plus 1. So the percentage of kinetic energy that is converted into the potential deformation energy is nothing but, how do I find out the percentage? Percentage is equals to initial kinetic energy minus final kinetic energy, that is the change in kinetic energy. This thing is, entire thing is nothing but the change in kinetic energy, no? Or the kinetic energy that was used to deform the body, divided by initial kinetic energy, isn't it? Now if I substitute the values, what percentage of kinetic energy used to deform the body, what is the value of initial kinetic energy? Or I can simply do as 1 minus final kinetic energy by initial kinetic energy. See, if I divide this by this, it is 1. If I divide this by this, it is final kinetic energy divided by initial kinetic energy. Okay, and what is the value of final kinetic energy? mv square by 4 sine square theta plus 1. What is the value of initial kinetic energy? Half mv square, half mv square, isn't it? So if I cancel out mv square and mv square, mv square, mv square, now 1 by 4 divided by 1 by 2 is nothing but 1 by 2, isn't it? 1 by 2. So it will become percentage of kinetic energy converted to deform the body is equals to 1 minus 1 by 2 sine square theta plus 1. Now what is the value of theta? 45. So sine square 45. Okay, what is the value of sine 45? 1 by root 2. Okay, and what is 1 by root 2 whole square? Is nothing but 1 by 2. So this will be converted to 1 by 2. 1 by 2 plus 1 is nothing but 3 by 2. So this entire thing is nothing but 3 by 2. And 3 by 2 into 2 is nothing but n is equals to 1 minus 3 by 4 is equals to 1 by 4. So 1/4 of the total kinetic initial kinetic energy would be converted to deform the body, or is used to deform the rubber balls. Okay.